According to a recent Gallup poll, about 36% of Americans say they are engaged at work. Suppose this is the true value of the proportion for the entire population, and we take a random sample of 100 Americans to see what percent of the sample say they are engaged at work. What is the probability that the result of the sample is within 5 percentage points of the population value? So this problem is about a sample proportion, so we should say what p hat equals. P hat is our symbol for sample proportion, and in this problem, p hat is the sample proportion that say yes in our sample. And our whole goal is we want to find the probability that p hat is within 5% of 36%. So if we write that symbolically, we're looking for the probability that our sample proportion then could be as low as 31%. So we could write it this way, saying that p hat is between 31%. And if it's within 5 percentage points of the population value, 36%, it could be as high as 41%. So we could write the probability we're trying to find this way. So before we find this probability, we have to see, is p hat normally distributed? And the way we do that is by checking the expected number of successes and the expected number of failures. They both need to be at least 10. So we look at how many people do we expect to say yes. And that is just our sample size times our probability. So we're sampling 100 Americans, 36% of which would say yes to this question, so we expect to get 36 yeses. So that is greater than or equal to 10, which is good. We also need the expected number of failures, or the expected no's, to be greater than or equal to 10, which is just the rest of the people. It's 100 people we're sampling. We expect 64% to say no. So that's 64 no's we expect, which is also greater than or equal to 10. So this will allow us to use a normal distribution to calculate probabilities about p hat. So next up, we need to find the mean and standard deviation of p hat, our sample proportion. And the mean of p hat, on average, our p hat is just going to be p, the population proportion, which for us is 36% in this problem, which should make sense. If I take a sample of 100 people, on average, it should be 36% saying they're engaged at work. But every sample is going to be a little bit different, and our standard deviation gives us an idea of how much each sample will vary. And the formula for the standard deviation of p hat is p times 1 minus p, all divided by n. We need that square rooted. You're only allowed to use this formula if the members in your sample are independent, and it's reasonable to assume these people are independent because our sample is so small compared to our population. It's supposed to be less than 10% of the population for the people to be independent, and there are certainly more than 1,000 Americans in the population. So it's safe to use this formula, and when we stick in our values, we have 0.36 for p, 1 minus 0.36, all divided by our sample size, which is 100. We need to square root that. And I'll bring my calculator over to calculate that out. So I'll do 0.36 times 1 minus 0.36. And I'll divide that by 100. And then I will square root that result. So our standard deviation comes out to be about 5%, a little shy of 5%. So now we have everything we need to calculate this probability, because we know that p hat's normally distributed, and we also know the mean and standard deviation of p hat. So off to the side here, I'm going to sketch a normal curve. And the mean of this normal curve is 36%. The standard deviation is almost 5%, 4.8%. And the goal all along was to find the probability that p hat is between 31% and 41%, within 5 percentage points of 36%. And looking at the standard deviation here, 5% is about 1 standard deviation. So I'm just going to estimate here. 31% is a little more than 1 standard deviation below the mean. And it's symmetric here. 41% is about 1 standard deviation above the mean. And we want to find the probability that the sample proportion is within 5 percentage points. So we're looking for this shaded area right here. And based on the 68, 95, 99.7 rule, this rule is really good for getting us estimates in problems like these. We know that if you go 1 standard deviation below the mean and 1 standard deviation above the mean, you get approximately 68% of data within those boundaries. So we know our answer is going to be about 68%, since our standard deviation is about 4.8%, and we're going within 5 percentage points. So I'm guessing the answer is going to be a little bigger than 68%. To figure out exactly what it is, you can use a table and you could convert 31% and 41% to z-scores, and you could look up these areas in a table. Or if you have a calculator, most calculators have a function that will calculate area under a normal curve. In the TI-84, you need to get to the distributions menu, which is above the variable button. So you hit second, distributions, and you use option number 2 here, normal CDF, to find shaded area under a normal curve. So I choose normal CDF. It asks you for 4 entries. It asks you for lower bound, upper bound, mean, and standard deviation. The lower boundary here is where I want to start shading on the left, which is 0.31. And the upper bound where I want to stop shading is 0.41. The mean we already found is 0.36, and the standard deviation is 0.048. And I'll paste this onto the screen and press enter. And there's our answer. And it makes sense based on the 68, 95, 99.7 rule. It's a little bigger than 68%. So I know that this probability is about 0.702, or if you like it better, you could call it about 70%. And that is the probability of getting a sample that is within 5 percentage points of the true population value of 36%.